Right, so picking up where we left off on 3.4, the eigenvalue method. Remember I said at the the end of the last lecture, that if you have an eigenvalue lambda and an eigenvector v, then you can construct a solution, a basis solution to your ODE. So let's do some examples of how to do that. So find the solution of the linear homogeneous system x prime equals x plus 2y, y prime equals 3x plus 2y. Okay, so the first thing that we can do is rewrite this as a matrix equation. We can rewrite this as x prime y prime equals 1, 2, 3, 2 times xy. So that will refer to as z vector prime equals a times z vector, where a refers to this 2 by 2 matrix, 1, 2, 3, 2. Okay? Let's try to find the eigenvalues of a. So to do that, we need to take the determinant of a minus lambda I2. In this case, and set that to 0. In this case, that's going to be the determinant of 1 minus lambda, 2, 3, 2 minus lambda. So you do have this determinant to get the characteristic polynomial. That's going to be 1 minus lambda times 2 minus lambda minus 3 times 2. So we should distribute that, and we'll get 2 minus 2 lambda, or actually 2 minus lambda minus 2 lambda plus lambda squared minus 6. This turns into lambda squared minus 3 lambda minus 4. That characteristic polynomial can be factored as lambda minus 4, lambda plus 1 equals 0. So then we get two eigenvalues, 4 and negative 1. Okay? So, now let's find the eigenvectors associated to lambda 1, which is 4. Okay, so the associated eigenvectors would satisfy the equation 1, 2, 3, 2 times, let's call it AB, equals 4 times AB. This is a plus 2b equals 4a, and 3a plus 2b equals 4b. Subtract a from both sides of the first equation and you get 2b equals 4a. Or 3a, sorry. And you'll find that you'll get the same thing if you subtract 2b from both sides of the second equation, because, again, these equations are going to be redundant. Okay, so then in that case, there's more than one way to figure this out. What I'm going to do is I'm going to say let a be 2 and b be 3. So this is my choice. If a is 2 and b is 3, then we have 6 equals 6, which of course is a true equation. So our eigenvector, v1, this is AB, and this is going to be just 2, 3. Now let's find the eigenvectors associated to lambda 2, which is negative 1. So those would be solutions of 1, 2, 3, 2 times, let's call it CD, equals negative 1 times CD. Okay, multiply through, you get C plus 2D equals negative C. 3C plus 2D equals negative D. Okay. So you subtract C from both sides of this first equation. What you'll get is 2D equals negative 2C, or in other words, C is negative D. So let's make the choice. Of D equals 1. In that case, the eigenvector v2 is going to be CD. This is going to be negative 1, 1. Okay. Now, how does that help us find the solution of this vector ODE? Well, all you have to do is take z1 vector is going to be v1 vector times e to the lambda 1t, and similarly z2 vector is going to be v2 vector times e to the lambda 2t. In our case, this is going to be z1 vector equals 2, 3 times e to the 4t, and z2 vector is going to be negative 1, 1 times e to the negative t. And as we discussed at the end of the last lecture, these are both solutions of this vector ODE, therefore this system, of course. So, according to our solution theorem, since we have a 2 by 2 matrix and 2 linearly independent solutions, the general solution is just all the linear combinations of those. So, what we get here is z vector equals c1 times 2, 3 e to the 4t plus c2 times negative 1, 1 e to the negative t. And that is at least one way of writing the solution of our system. Okay? So this is always how these examples work. You convert your system into a matrix ODE. You find the eigenvalues and eigenvectors of that matrix, construct the basis solutions based on the eigenvalues and eigenvectors, and then just take all the linear combinations. And that's that. So of course we're going to do some more examples. Let's see. Let's suppose we have x prime equals x plus 2y. Y prime equals 3x plus 2y. Wait, this is the example that we just did. Yeah, this is... Ah, it appears that in my notes I have the same example twice. Well, that's perplexing. Okay, new example now. Let's say we have the vector ODE z prime equals -5, 1, 4, -2 times z vector. And once again, we'd like to find the solution, the general solution of this matrix ODE. By the way, I should have said over here, this is the general solution. So this is the general solution. You know it's the general solution because you have these arbitrary constants in it. Okay? Just like scalar ODEs, matrix ODEs have general solutions and particular solutions. So yeah, we're going to try to find the general solution of this matrix ODE. So once again, I'm going to call this thing A in order to avoid writing it over and over again. We need to find the eigenvalues of A. So we need to take 0 equals determinant of A minus lambda I2. In our case, that's going to be the determinant of -5 minus lambda, 1, 4, -2 minus lambda. You multiply through, you get here -5 minus lambda times -2 minus lambda minus 4 times 1. Okay. Then this becomes 10 plus 5 lambda plus 2 lambda plus lambda squared minus 4. Yeah. So clean this up a little bit, and this looks like lambda squared plus 7 lambda plus 6. And then that characteristic polynomial can be factored. We can write this as lambda plus 6, lambda plus 1. To get the eigenvalues, lambda 1, which is -6, and lambda 2, which is -1. Okay. So those are the eigenvalues. And by the way, I just want to point out that in the examples that we've done so far, this one and the previous one, they've been distinct real eigenvalues. They won't always be distinct real eigenvalues. We're going to talk about non-real eigenvalues later today and multiple eigenvalues in a future lecture. But in any case, for right now, we have distinct real eigenvalues. Okay. So let's try to find the eigenvectors associated to lambda 1, which is -6. So those would be solutions of the equation -5, 1, 4, -2 times, let's call it AB, equals -6 times AB. Multiply through, and we get -5a plus b equals -6a. 4a minus 2b equals -6b. Add 5a to both sides of the first equation, and you get b equals -a. And of course, you get the same result from the second equation, too. So let's make the choice. A equals 1, for no particular reason. In that case, the vector v1, which is AB, is going to be 1, -1. Okay. Next up, let's find the eigenvectors associated to lambda 2, which is -1. Those would be solutions, let me draw a partition here so we don't get confused. Those would be solutions of -5, 1, 4, -2 multiplied by AB equals -1 times AB. Multiply through, you get -5a plus b equals -a. 4a minus 2b equals -b. Let's see here. I guess I'd like to add 5a to both sides of the first equation so that we can get b equals 4a. So now make the choice. A equals 1. Again, for no particular reason. V2 vector becomes AB. Oh, I just realized I wrote AB for both of them rather than AB and CD. Not that that matters much, right? But in any case, this becomes 1, 4. Right, so these give rise to two basis solutions. Z1 vector equals V1 vector times e to the lambda 1t, which in our case is going to be 1, -1 times e to the -6t. And then Z2 vector, this is going to be V2 vector e to the lambda 2t. So that's going to be 1, 4 e to the -t. Okay. And then the general solution is just all the linear combinations of those. So z vector, the general solution, is going to be c1, 1, -1, e to the -6t, plus c2, 1, 4, e to the -t. And that is our general solution. Now, as I said, the eigenvalues are not always real and distinct. So let's do some examples where you have complex eigenvalues. In that case, we're going to have to use Euler's formula to convert them into a better form. So, the directions are still the same. Find the general solution. But of course, the matrix is going to be different. So let's say we're trying to find the general solution of z vector equals 2, 1, negative 1, 2 times z. Or z vector prime equals 2, 1, negative 1, 2 times z vector. So, first thing we're going to have to do is find the eigenvalues. So that requires the determinant of a minus lambda I2, which in our case is going to be the determinant of 2 minus lambda, 1, negative 1, 2 minus lambda. You multiply through, you get 2 minus lambda times 2 minus lambda minus negative 1 times 1. This becomes 4 minus 2 lambda minus 2 lambda plus lambda squared plus 1. In other words, lambda squared minus 4 lambda plus 5. Okay. So you look at this for a moment and you realize that it can't be factored, so you use the quadratic formula. Lambda equals 4 plus or minus the square root of 4 squared minus 4 times 1 times 5 divided by 2 times 1. This is going to be 4 plus or minus the square root of 16 minus 20 is negative 4. Divide this by 2. So this becomes 4 plus or minus 2i divided by 2, or in other words, 2 plus or minus I. Okay. So now we need to find the eigenvectors. Let's see here. Those would be solutions of 2, 1, negative 1, 2 multiplied by AB equals 2 plus I multiplied by AB. You multiply through, you get 2a plus b equals 2 plus I times a, and negative a plus 2b equals 2 plus I times b. Subtract 2a from both sides of the first equation and you get b equals I times a. So let's make the arbitrary choice. A equals 1, in which case our eigenvector AB becomes 1i. Okay. So now, what do you do about the solution that this generates? Well, as usual, we're going to look at z vector, which is v vector e to the lambda t. And in our case, that's going to be 1i times e to the 2 plus I times t. So first of all, this can get rewritten as 1i multiplied by e to the 2t multiplied by e to the it. And then the e to the 2t we'll just put in front because it's real valued and won't matter much. E to the it, according to Euler's formula, is cosine of t plus I times the sine of t. So we have e to the 2t, 1i, cosine of t plus I times the sine of t. Multiply through, you get e to the 2t multiplied by cosine t plus I sine t, and I cosine t plus I squared sine t. Now, what is I squared? Well, as everyone knows after learning about imaginary numbers for the first time, I squared is -1. So this becomes e to the 2t times cosine of t plus I sine of t, negative sine t plus I cosine t. Separate this into two vectors, one for the real part and one for the imaginary part. So this is e to the 2t times cosine t, negative sine t, plus I times e to the 2t, sine t, cosine t. And now, just like with linear homogeneous ODEs with constant coefficients, the real and imaginary parts individually form our basis solutions. So the general solution then is going to be C1 e to the 2t cosine t sine t, or negative sine t actually, plus C2 e to the 2t sine t cosine t. And that is our general solution. Okay? So when you have non-real, I should say, when you have non-real eigenvalues and non-real eigenvectors, what you'll have to do is apply Euler's formula in order to get a linear combination of the real and imaginary parts. Then those form your basis solutions. Okay? So let's do another example. This one is, let's see here. So let's say we have x prime equals x minus y prime equals 5x minus y. We're going to try to find the general solution. So, as usual, we can convert this to a matrix equation. Z vector prime equals 1, negative 1, 5, negative 1, times z vector. We need the eigenvalues of this matrix. So 0 equals determinant of A minus lambda I2, which is going to be the determinant of 1 minus lambda, negative 1, 5, negative 1 minus lambda. You do the determinant, you get 1 minus lambda times negative 1 minus lambda minus 5 times negative 1. This turns into negative 1 minus lambda plus lambda squared plus 5. Ergo, we get here lambda squared plus 4. That gives us the two complex roots, plus or minus 2i. Okay? So those are the eigenvalues. Now let's find the eigenvectors associated to one of them. So lambda equals 2i, we'll say. We're looking for solutions of the equation 1, negative 1, 5, negative 1 times AB equals 2i times AB. Multiply through, you get A minus B equals 2i times A. 5a minus b equals 2i times b. Okay. Add b to both sides of the second equation to get 5a equals 1 plus 2i times b. And then let's make the choice a equals 1 plus 2i, so that b will be 5. So then our eigenvector, AB, is going to be 1 plus 2i, 5. All right. So then once again, we have to consider v vector e to the lambda t. In our case, that's going to be 1 plus 2i, 5, e to the 2i times t. E to the 2i times t can be rewritten using Euler's formula. This becomes 1 plus 2i, 5, cosine 2t, plus I times the sine of 2t. Multiply through. You get 1 plus 2i times cosine of 2t plus I times the sine of 2t, and 5 cosine 2t plus I times 5 sine 2t. You distribute the first coordinate. This becomes cosine of 2t plus I times the sine of 2t plus 2i cosine of 2t plus 2i squared sine of 2t. I squared is negative 1. And then the second component is still 5 cosine of 2t plus I times 5 sine of 2t. This turns into cosine 2t minus 2 sine 2t, 5 cosine of 2t, plus I times sine of 2t plus 2 cosine of 2t, 5 sine of 2t. And then, once again, our basis solutions are the real and imaginary parts. So then our general solution is C1 cosine 2t minus 2 sine 2t (5 cosine of 2t) plus C2 sine of 2t plus 2 cosine of 2t, 5 sine of 2t. And that is that. Okay, so this is how it works when you have non-real eigenvalues. You find the eigenvalues, find the associated eigenvectors, which are probably going to have a non-real part, then do Euler's formula to rewrite v e to the lambda t as a linear combination of a real vector and an imaginary vector. And then those real and imaginary parts become your basis solutions. Anyway, that's all for today. See you in the next one.